the idea that when one does a Lorentz transformation, the electric and magnetic fields that are seen in co-moving frames are different from those fields that are seen in some initial inertial frame. And the way that we saw that was the fact that the sources of E and D change in different reference frames. So in particular, the sources of E and B, which are the charge density and the current density, transform into again when we go to a new reference frame. And because of that, there is a different electric field and magnetic field seen in that other reference frame. And what we found were fairly complicated transformation laws for the E and D fields, which I don't remember, so I'll write them here. So the signs that I always forget. But anyway, what we found was that the component of the electric field that is perpendicular to the direction of the boost transforms as such. So we boost the velocity v, and we find that the electric field transverse component changes like that, but the parallel component remains unchanged. And the magnetic field changes as such. Now, these transformation laws are not at all obvious, and they don't look like the transformation laws that we saw for a Lorentz transformation with a spatial component and a time-like component. So the combination of charge and current together form a 4-vector, which transforms according to Lorentz transformation, where C rho prime is equal to gamma C rho minus V, let's say in the x direction, Jx, and Jx prime is gamma Jx minus V rho. So that's the transformation of the sources is equivalent to the transformation of space and time, and so together they form a 4-vector. But the components of E and B don't do that. So there's something more that we need in order to be able to understand these transformation laws from first principles. All right? So, how are we going to get at this? Well, in order to do that, we need to step back for a minute and remind ourselves, or see for the first time, depending on what your exposure was in the past, what we mean by non-Euclidean geometry. So why do we have to worry about non-Euclidean geometry? Well, what motivates this is the fact that what we find is that space-time geometry is not Euclidean. Why is that? Well, what we found was that an invariant space-time interval between two events was this. And that interval is not a Euclidean interval, right? So in Euclidean geometry, what we mean is that we say, well, let's say we have an arbitrary number of dimensions. Let's say we have the space Rn. So we have n dimensions, however many we want. And we have some point in Rn that's a vector. Okay? And we can express that point in the space in terms of a basis. So we have some basis for the space, e sub I going from 1 to n. And we can decompose x in terms of those basis vectors. And then we're going to now have this convention that we'll explain in more detail of summing over repeated indices where one of the index is lower and one of the index is upper for reasons that will become more apparent in a little while. Okay? But first I need to wash down that delicious coffee cake. Some coffee. Not wash down, but a compliment. Because I've been savoring it. All right. So, so we have this space, we have some x. Now, a vector space, by definition, mathematical definition, is just defined in terms of linear superposition and multiplication by scalars. A vector space on its own has no notion of distance. The notion of distance is endowed upon the space by some definition. Okay? So the notion of distance, so we define length or distance. So for example, we can say, what is the distance of this point from the origin? Which is the length of that vector. Now, if it's Euclidean, so the length of x, distance from origin, is defined, let's say the length itself. If it's Euclidean, then that distance is defined by Pythagoras' theorem. That's the definition of the Euclidean distance. So we have the 1 coordinate squared, the 2 coordinate squared, whatever the event coordinate is. So that's a definition. Okay, so that's what we mean by the distance. Now, once we have the distance, we have a new structure on our vector space. We have the notion of, so that once we define a length, we have a notion of inner product. So the inner product is an extra doodad, it's an extra ornamentation that one puts upon a vector space. Not every vector space has an inner product. But once we define length, we have inner product, because by definition, we define the inner product or dot product as the length squared. Okay? So that's equal to this. Now, given the fact that our vector in the space can be decomposed into a basis, this tells us something about the relationship between inner product and distance, tells us something about what we are defining the inner product to be between different basis vectors. Because if I plug this in, so I have xi, ei, dotted into the vector. Now I'll use a new w index, j, ej, which is xi, ei, dot ej, xj. Okay? This is an array of numbers, gij. Okay? It's a matrix with matrix elements given here. And that matrix is known as the metric. It's a way of converting coordinates to distance. Okay? Now, all of this is incredibly heavy-handed in the context of Euclidean space. I mean, because in the context of Euclidean space, if it's Euclidean, if this is going to be what we mean by distance, then the metric is trivial. In other words, the matrix is the identity matrix. We didn't need to introduce a new concept called metric. It was, the dot product is these are orthogonal vectors. But if our notion of distance has a metric which is not the identity, in this case we see the metric in our space-time, the way that we define distance here, the metric is 1, minus 1, minus 1, minus 1. Right? Because to get distance, we have to, between space-time events, we have these minus signs here. Which means that space-time is not Euclidean. Space itself can be Euclidean. I mean, the overall sign here is irrelevant. I could have put a minus sign here and plus here. That would have been the same thing. It's irrelevant. But if I'm going to have space and time together, one of them's got to be negative and the other one's positive. Which means that space-time in special relativity is not Euclidean, and true in general relativity. In this case, in special relativity, it's so-called a flat space-time. It's Minkowski space. So, what we're going to do today is describe a little bit of the mathematics that's behind thinking about non-Euclidean geometry and how we talk about vectors and tensors in that space. Yeah?
I'm new at this, so what it looks like is the superscript or subscript represents row vector, column vector.
No, they're not that.
No?
There's a few rules, we'll get at them. But the rule here is that we're going to sum over repeated indices where one index is an upper index and one index is a lower index. The meaning of upper and lower is not at all apparent yet. There's, why the heck did I put this guy up and this guy down? There's no reason yet, except it's a rule, and it'll become clearer. Now here, this is, I can rewrite this if I like, as matrix multiplication, where I think about this as, you know, I can have a vector with these guys, okay? In which case, this summation could be rewritten as in other words, if I were to write this out, I have the column, the row vector so I sum over repeated indices, and by the rules of matrix multiplication, that means I sum a column with a row with a column. Does that make sense? So upper and lower are not row and column yet. Well, not ever, but we don't know what they mean yet.
So
Yeah.
if I have n-dimensional Minkowskis, they're all going to be negative.
If I have n spatial and one time, yes. These got the way this. The overall, all that matters is the determinant of the matrix. This is called signature of the matrix. I could have made this guy negative and all of these positive. You may have in elementary modern physics done the most nauseating ICT notation for faking the minus sign by putting an I in, because when you square an I, then you can make it look like Minkowski space with an I in it. Make one of these, when you square it, becomes -1. Have you ever done that? Yeah.
So wow. Is there any so besides, some sort of aesthetic, distaste for it, the throwing in the I, is it bad just because it obscures the metric? Or?
Yeah.
Okay.
That's why I think it's bad.
Okay.
It's bad because it's impossible then to generalize to general relativity, because you have no idea where the heck this is coming from.
Yeah.
But no, as far as manipulation goes, it's perfectly fine and useful.
Okay.
But there's no, I don't know, aesthetically it makes my stomach churn. And you don't want to see that.
It's on the cake.
No, it's definitely not the cake. Cake is the best ever.
Cake's the only thing that soup does.
Exactly. All right. Right. So now let's look at an example, a simple example of a non-Euclidean geometry. Okay. So suppose I took as, I'm just going to look at a two-dimensional space, but a two-dimensional non-Euclidean geometry. Okay? So I'm going to define two basis vectors, E1 and E2. Okay? This is a basis for the space. I can look at any vector in the space. Here's an example of a vector, x, which can be decomposed into some amount of the first basis vector and some amount of the second basis vector. Okay? And here it is. It's got some amount of this and some amount of that. Okay? In fact, we know from the law of cosines that the length squared of that is x1 squared plus x2 squared plus 2 x1, x2 cosine alpha. Right? Where if alpha is the angle between those two basis vectors. And in fact, that agrees with our definition of length, where the metric, well, is di dot dj. And that metric, we can easily write down what the metric matrix is. Taking these each to be unit vectors. I mean, this is a non-Euclidean space that we can visualize because I've embedded it in Euclidean space, and we're borrowing the Euclidean notions to get the picture of what's going on. But I didn't have to draw the picture. I could have just defined this to be the matrix, which is 1 on the diagonals and cosine on the off diagonals. Notice the metric is always a symmetric matrix because this is equal to EJ dot EI, because the dot product is symmetric. So that's the metric, and that's how we calculate distance, and it works, right? All right. We're going to use this example to build our whole jargon and notation about covariant and contravariant and dual bases and all of that stuff in today's lecture. All right, so this is a simple example of a non-Euclidean geometry. Now, an important notion is a change of basis. So let's suppose I have a transformation that gives me new basis vectors through some transformation I'll call gamma j dj, some over repeated indices. Okay, so we have two bases, the unprimed and the primed bases, and this is the relationship between those bases. Okay, now we can ask the question, what is the condition on this change of basis matrix such that the metric is preserved, and thus distance is preserved relative to the new coordinates. So a change of basis matrix, or so if the transformation preserves the metric by lengths are preserved, respect to the new coordinates. That is to say, if I have this vector in the space which has coordinates with respect to the original basis, it also can be decomposed with respect to the new basis. And the length squared by definition was that. What we want is we want to look for the set of transformations such that this, with respect to the new coordinates, I use the same metric. The condition, the question is, what is the condition on the transformation matrix such that this is true? Well, it's a fairly trivial thing to see. The new metric with respect to the new basis, is that we want this to be equal to the old metric. So that tells us, now we got to make sure we don't reuse the dummy indices. These are free indices, and this is a summed over index. And the whole trick in playing with this tensor algebra is always make sure you know what's a fixed index and what's a dummy index. So we need a new index. So we have gamma ik ek dotted into gamma j l e l. Okay, the dot product's linear. These are just numbers. They come through. And this is GKL. So the condition that the new metric is the same as the old metric, that the metric is preserved, is the condition that written as a matrix, notice this was row column. We're summing over L. In order to do this as matrix multiplication, I have to take the transpose so that I sum a row with a column. So written as a matrix, this says that the condition is that the transformation matrix gamma times the metric matrix times its transpose, i.e. a similarity transformation, keeps the matrix unchanged. Okay, so if the metric is unchanged by a similarity transformation, then distance is preserved. Okay? Now, for the case of Euclidean geometry, the metric is just the identity. So the condition that the transformation doesn't change distance is the condition that gamma is an orthogonal matrix. That is to say that its inverse is equal to its transpose. Okay. That is a so-called orthogonal transformation. So the set of transformations which preserve distance in Euclidean space are the orthogonal transformations, and they are rotations and reflections. But for a more general geometry, we have this condition for the notion of a transformation that preserves distance. Yeah?
So this might be like kind of an ill-posed question. So
I'm ready.
just let me know if that's the case.
I don't know if you guys are ready, but go on.
But yeah, so it seems like in this context, like when we're changing bases, so you've got your matrix gamma represents a changed basis, and the inverse always represents changing back to your original basis from your new basis. But is there any easy, or easily visualizable, general relation between what, a change of basis matrix represents versus what its transpose represents?
No.
Okay.
No, they're not. I mean, the transpose, what we're about to show is that the transpose of the inverse has a meaning,
Okay.
an important meaning. But the transpose itself is not related to anything special. Only for Euclidean geometry is the
Okay.
transverse equal. All right, the reason I say the transpose of the inverse is important is what we defined gamma to be was the thing that changed the basis vectors. Okay? This is an active transformation that takes one vector to another. We can ask a different question, which is, once I change the basis, what are the new coordinates of a fixed vector with respect to the new basis? In other words, so this is what's called an active transformation. It actually moves a vector to a different vector. Okay? But I can ask a different question, which is, suppose I have, now I'm going to ask about a passive transformation, which is a transformation on the coordinates. So what I mean by this is, let's suppose I have some point in space, which can be decomposed in terms of some basis, so it has some coordinates. But it's the same vector, but it has a different representation. In other words, it has coordinates with respect to the new basis vectors. So the basis vectors have shifted, but the vector hasn't. It just has new coordinates with respect to that. Is that clear, the difference? So now I want to ask the question, what are these new coordinates with respect to the old coordinates for the same vector? That's a change of coordinates. So, well, we know that. We just said, we know how to transform the coordinates. That's gamma ij. Well, let me use a different dummy index here so I can see this more clearly. JJ, it doesn't matter. It's the dummy index, but it'll make the algebra a little bit easier. J gamma J I E I. Okay? So this was the transformation of the new basis vector in terms of the old basis vectors. Okay? So what we see here is, can rewrite this as gamma J I transpose it's the same numbers, but okay, just writing it on the other side. But I can look at this now and see this as a matrix equation. The column vector, which I'll call x tilde, is equal to the transpose of this matrix multiplied by the column vector of the prime coordinates. Okay? So, what we've learned from this is that the new coordinates are related to the old coordinates by the inverse of the transpose of that matrix. We saw this in the first week of class, and I said, don't forget it. We've all forgotten it. But I have the evidence. Podcast 2. seek it out. When we're talking about tensors. But what we see here is that these coordinates, xi, transform as a new system. Okay? Now this inverse transverse matrix we call lambda. So what we see here is that the basis vectors and the coordinates don't transform the same generally. One transforms according to gamma, the other transforms according to lambda, and they are related. One is the inverse transpose of the other. However, for Euclidean geometry, gamma equals lambda, because the inverse transpose gives you back the vector, I mean the matrix again. So there's no distinction. That's why this seems so, what the heck is this? I mean, we never do this in vector algebra. What are you telling me about inverse transpose? Because it doesn't make a difference. We don't make this distinction in Euclidean geometry because there is none. Notice that that means there's a slightly different way that this can be written. If I write this, if I multiply it by multiply both sides by the inverse, then that gives me another way that you'll often see this written. Okay. All right. So, let's see. What's the next? Oh yeah, I guess one thing we can see immediately from this relationship here is what this transfer matrix is. Because I can just take the partial derivative of this equation with respect to these coordinates. So this tells me that this transformation matrix on these coordinates x super I is the partial derivative of the prime coordinate for the ith component with respect to the unprimed coordinate. So if I know how the coordinates transform, then I have the transformation matrix according to that Jacobian. Moreover, if I look at the gamma matrix, so let's take the transpose of this and then take its inverse. So that's the transpose of this is switching J and I. And then I'm going to take its inverse. And the inverse, of course, is just 1 over these derivatives. All right? Okay, now the next concept that we want to introduce that's important is the notion of the dual basis covariant and contravariant coordinates. So to do that, let's return to our very simple example of the 2D non-Euclidean geometry where our basis vectors were non-orthogonal to one another. Okay? Given a basis, we can define a so-called dual basis, which has superscripts such that the inner product between a vector in the basis set and a vector in the dual set are bi-orthogonal. In other words, E1 dotted into E1 superscript is 1, but E1 dotted into any other thing superscript is 0. Okay? So, for example, if I draw my original basis, what does the dual basis look like? Well, here it is. This is my E1 superscript. It's perpendicular to this. And E2 superscript is that guy.
I think it's the other way around.
What's that?
I think because it seems like right now E1 superscript dot E1 subscript.
Oh, I'm sorry. This should be E2. Right. And this should be E1. Pardon me. Thanks, David. All right. So these are the dual vectors, and their lengths have to be such that they're normalized, E1, in the appropriate way. But that's fine. Okay? Is that so? Of course, for Euclidean geometry, the vectors are self-dual. Okay. But in a non-Euclidean geometry, they're not. All right. Well, what can we say about this? Well, firstly, what that means is that since both of these bases span the space, we have different sets of coordinates. We have a set of coordinates with respect to the original basis, and a set of coordinates with respect to the dual basis. So I can write x, as we said, as a superposition of the original basis vectors, but we can also write it as a superposition with respect to the dual basis. So we have two sets of coordinates, one with superscripts and one with subscripts. In Euclidean geometry, they're the same set of coordinates because the dual is itself. But in a non-Euclidean geometry, they're different coordinates. They represent the same point in space, It's just the decomposition of some vector x with respect to this basis is different from its decomposition with respect to the dual basis. Okay? All right, so now what we want to do is understand how, let's see, there's a number of things we could say. I guess the thing I'll do next is to ask the question, how do the dual vectors transform given we know a certain transformation on the original vectors? That's to say, let's suppose we have some transformation that keeps the metric fixed, changes these vectors in some way to some other vectors. The dual vectors have to change as well in order to maintain the metric. So, transformation on the dual basis. So the dual basis is defined such that they're bi-orthogonal. Okay. Now, this guy transformed according to that matrix we call gamma. Let's say this thing is some new matrix A, or capital alpha. All right, so these dot this into that, I get a delta function KL, so I get A J K is equal to delta IJ. Okay, but the matrix, this says that gamma times A transpose is the identity. But the thing which is the inverse transpose is what we call lambda. So the moral of this story is that A is equal to lambda, and thus the dual vectors transform according to the lambda matrix. How do the coordinates with the lower subscript transform? Remember, we also said that x of I transform according to this. This should be prime. Everything is prime. So how do the coordinates with respect to the lower transform? Well, we have this. That was the initial definition. And with a little bit of algebra, and it doesn't take much algebra at all to show that the coordinates with respect to the lower subscript transform according to the inverse transpose of this. Thus, these sets of coordinates are given certain names. The coordinates that transform with the original basis are covariant. They transform with the basis vectors in the same way as the basis vectors. So these are called the covariant coordinates. The guys that have the upper subscript transform as the dual basis vectors transform. And thus, they are called the contravariant coordinates. So, given a geometry that is generally non-Euclidean, I can express the coordinates of that vector either respect to some basis or its dual. I can either talk about its contravariant coordinates or covariant coordinates. Now you probably have heard about covariant and contravariant coordinates, but did you ever know why they were called contra and co? That's why. All right. Now we can look at this. Why is geometrically is there some? Why are there these two different sets of coordinates and two different basis vectors when we have a non-Euclidean geometry? It's because really there are two different notions of vectors. There's a notion of displacement and a notion of normal. Normal to a level surface. And the covariant and contravariant components correspond to either displacing along the level surface or being normal to a level surface. Let's draw a picture. So I can talk about, here's a non-Euclidean grid. I hope it works. Let's see, do we have any color chalk here today? Or the one day I want some. Let me go get some. I'll be right back.
My secret stash. We have a secret stash. There's coffee and there's cake if you guys want some.
Don't tell everybody else. Put it all
I
over
didn't
someone.
just make it for you guys.
We were here earlier. Worthy of it.
It's hidden in plain sight.
What? Oh, yeah.
Yeah, rain for cake is good. Well, we got pukey color, so.
Well, hold on.
Ooh. Oh my God, it's like hopscotch. So we have these original vectors, E1 and E2. We have, well, so we have surfaces of constant value of E1 and surfaces of constant value of E2. Okay, so that's a grid on this space that's non-Euclidean, right? Now we can ask, what about the dual vectors? Well, we got the guys that are dual to this. So let's see. They were. So there's two grids, and you see there's a biorthogonal value, right? The pink are perpendicular to the blue, but the pink are not perpendicular to one another, and the blue are not perpendicular to one another. We have a vector which tells us how to get from one blue curve to another blue curve, and we have a vector which tells us how to displace along a blue curve, or displace along a pink curve. Okay? So, on PP color. So a displacement along x1 these are contravariant coordinates because they are perpendicular to surfaces of constant x1. So a vector that tells me how to displace in space is related naturally to contravariant coordinates. And we can see that if I have dxi are the displacement coordinates. And I want to know what are the displacements with respect, I do a change of basis. Well, according to the chain rule, that's that. And we just said that this matrix written over there is what we call lambda. So displacements are, their natural coordinates are the contravariant coordinates. If I want to look at a translation along a constant x1, the generator of translations along constant x of I, whatever that is, well, that generator is the derivative. Remember that from late mechanics, quantum mechanics, right? The momentum operator translation is a derivative operator. So, if I think about this kind of vector, this is the ith component of gradient. And I want to know, how does this transform? So I go to a new basis, I have new coordinates. Well, according to the chain rule, that's equal to that. And this is what we call gamma ij, the inverse transpose. So what we learn here is why in the world we put upper and lower coordinates on this thing. The reason we put upper and lower coordinates up here is that the derivative with respect to an upper coordinate is a lower coordinate, because it's in the denominator. Of course, if I took the derivative with respect to the covariant, I would get the contravariant. So, the gradient is naturally a vector whose coordinates are covariant because they represent translations along a constant coordinate. And displacements are the other notion of vector going from one level surface to another, and their components are naturally contravariant. All right. Now, there is a way that you can get your exercise and go from lower coordinates to upper coordinates and upper coordinates to lower coordinates. But you can't do sideways, that's required. Sorry. I want to do the polarization dance for you, that's the spring of the class. All right. We did the polarization dance. All right. So, bless you, bless you. How are covariant and contravariant coordinates related? Well, let's suppose I have some vector. It can be decomposed in terms of its contravariant coordinates, or it can be decomposed in terms of its covariant components with respect to the dual basis. Now let's suppose I take the dot product of this with respect to the basis vector E sub j. All right. This is, by definition, a delta function. So this is xj. And this, by definition, is the metric matrix. So what we see here is that to get from from upper index to lower index, I have to multiply by the metric. The metric basically transforms me from covariant to contravariant coordinates. In Euclidean geometry, they're the same thing because this is the identity. But in a non-Euclidean geometry, they're not. Of course, this is symmetric, so I could write it the other way around. It says xj is equal to sum over I. Similarly, G I J upper indices is that equal to that dot product. And I can get covariant to contravariant by multiplying through the matrix of the metric. All right, so a few more things for today. today's lecture. For next lecture, we'll apply this to electricity and magnetism. So generally, so we've defined this in terms of position in a space, but we could talk about general vectors and tensors in a non-Euclidean space. So I can define a vector as a collection of 3 or whatever n coordinates, which can have covariant or contravariant coordinates. As I say, the vector is the same. There's some basis, whether I write it in its covariant or contravariant decomposition. And it's a vector if that's true, then the covariant components transform according to that transformation, and the contravariant components transform according to this transformation. So it's the same transformation matrix that that position transformed as. If it transforms that way, we call it a vector. We can talk about tensors. Tij is a rank 2 tensor. And with respect to a new basis, the components of that tensor transform where each component transforms according to a transformation matrix. We can also have a way of going between up and down indices. So as before, Vi is the metric tensor times Vj with the upper index. I can talk about mixed index tensors with one lower index and one upper index. And that would be obtained by lowering the first index with the metric tensor. Or I can lower both indices. I sum over the appropriate index, or vice versa. And each upper index transforms according to this, and each lower index according to the inverse transpose. All right, let me conclude with this to say now, what does this mean for Minkowski space? So, Minkowski space. Is 4-dimensional. And as we define, the metric matrix is diagonal with all the spatial components the opposite sign of the temporal component. Okay? How do we know that this is the metric tensor? Because this is the metric that is invariant under change of inertial frame. Remember, still written over here, we define the set of transformations that preserve the metric as the set of transformations that satisfy the similarity transformation. We could then ask a different question. Given that the transformation is the Lorentz transformation, which could include a boost or a rotation, what is the metric that is preserved by the Lorentz transformation? And the answer is that one. So this transformation is preserved under the Lorentz transformation. So we define the Lorentz transformation as, so these are the, this is the matrix elements. And the matrix, for example, a boost along X was gamma minus gamma beta minus gamma beta gamma 1 1 0 0 0 0 0 0. This metric is preserved under these transformations. And from that, what we see is that the fact that this is true, that delta S squared, which is equal to x0 g, or x mu g mu nu x nu. Oh, so remember, mu and Greek letters go 0, 1, 2, 3. 0 is the time component, 1, 2, and 3 are x, y, and z. This is the distance. Let's just write that out and then we'll quit. So the claim is that the distance, the Minkowski distance between two space-time events, delta S squared, is delta x mu, the x mu, so which is equal to x mu g mu nu delta x mu, right? Because I can lower index, summing over two indices, lower one, raise one, put a g mu nu in the middle. That's equal to x0 squared minus x1 squared minus delta x2 squared minus delta x3 squared, which is c squared delta t squared minus delta x squared plus delta y squared plus delta z squared. Is that clear what I did? So this is the metric. This metric is invariant under a Lorentz transformation. And so this defines what we mean by Minkowski space. Moreover, any vector which transforms according to this is a 4 vector. And its norm squared is the scalar product with one upper index and one lower index, which is equivalent to that, which is equal to which is Lorentz invariant. Because by definition, the Lorentz transformation preserves this length. That's how we got the metric. And we can define tensors and all the rest. And we'll conclude this tomorrow. Anybody else?